Today I want to discuss the hydrogen energy sources. In the first part of my I want to discuss the introduction to the hydrogen energy, application of hydrogen energy and the hydrogen production methods. In the second part of my lecture, I want to discuss the storage of the hydrogen energy, transportation of the hydrogen energy and the advantages and disadvantages of the hydrogen energy. To the introduction part of the hydrogen energy system. The hydrogen is the simplest element. It is also the most plentiful element in the universe. An atom of hydrogen consists of only one proton and one electron. Despite its simplicity and abundance, the hydrogen does not occur naturally as a gas on the earth. It's always combined with the other elements. Water, for example, is a combination of hydrogen and the oxygen. The hydrogen is also found in many organic compounds, notably the hydrocarbons that make up the many of our fuels, such as gasoline, natural gas, methanol, and the propane. The hydrogen can be separated from hydrocarbons through the application of heat, a process known as the reforming. Currently, most hydrogen is made this way from the natural gas. An electrical current can also be used to separate the water into its components of oxygen and hydrogen. This process is known as the electrolysis. This is very much common to all. Some algae and bacteria using the sunlight as their energy source even give off the hydrogen under the certain conditions. Hydrogen is higher in energy, yet an engine that burns pure hydrogen produces almost no pollution. Hydrogen is considered as the alternative fuel. It is due to its ability to power fuel cells in the zero emission electric vehicles, its potential for the domestic production and the fuel cells potential for high efficiency. In fact, a fuel cell coupled with an electric motor is 2 to 3 times more efficient than an internal combustion engine running on gasoline. Hydrogen can also serve as fuel for internal combustion engines. The energy in 2.2 pounds of hydrogen gas contains about the same as the energy in 1 gallon of gasoline. NASA has used the liquid hydrogen since the 1970s to propel the space shuttle and the other rockets into the orbit. Hydrogen fuel cells power the shuttle's electrical systems, producing a clean byproduct, pure water, which the crew drinks. A fuel cell combines hydrogen and oxygen to produce electricity, heat, and the water. Fuel cells are open compared to batteries. Both convert the energy produced by a chemical reaction into a usable electric power. However, the fuel cell will produce electricity as long as the fuel is supplied, never losing its charge. Fuel cells are a promising technology for use as a source of heat and electricity for buildings and as an electrical power source for the electric motors propelling vehicles. Fuel cells operate based on the pure hydrogen. But the fuel like natural gas, methanol or even gasoline can be reformed to produce the hydrogen required for the fuel cell. Some fuel cells even can be fueled directly with the methanol without using a reformer. In the future, the hydrogen could also join the electricity as an important energy carrier. An energy carrier moves and delivers energy in a usable form to the consumers Renewable energy sources like the sun and wind cannot produce the energy all the time, but they could, for example, produce electric energy and hydrogen, which can be stored until it's needed. Hydrogen can also be transported to the locations where it is needed. This is the hydrogen cycle. The hydrogen, there is some conventional renewable sources are there, the nuclear powers are there, fossil fuels are there, but there is another resource, is the hydrogen energy. The hydrogen is generated by some processes and it is applied in the hydrogen vehicle as a fuel, synthetic fuel, upgrading well at the biomass, ammonia fertilizer, the metal refining and the other end uses, and for heating the hydrogen gas is used. And also in the gas infrastructure the hydrogen gas is used. This is the application of the hydrogen gas, and also it is used to generate the power to the power grid. The applications of hydrogen as an energy source in India. The current source of hydrogen production in India, the hydrogen is a byproduct of core alkali industries. Earlier a part of it was used for the non-energy applications and rest was either flared or vented out in the atmosphere. With the passage of time, awareness about its usage for energy applications increased, and up to the 2013 the 14 around 90% of the byproduct hydrogen was utilized for the production of chemicals and the captive applications. Hydrogen is produced for the non-energy applications like in fertilizer industries and the petroleum refineries. The National Hydrogen Energy Roadmap, that is called NHERM, as per their report, with a view to accelerate the development of the hydrogen energy sector in India, a National Hydrogen Energy Roadmap was prepared and adopted by the National Hydrogen Energy Board in January 2006 for the implementation. Now the very important stage of my lecture, that is the hydrogen production methods. The hydrogen production is the family of the industrial methods for generating the hydrogen gas. As of 2020, the majority of hydrogen, approximately 95% of it, is produced from the fossil fuels by the steam reforming of the natural gas, partial oxidation of the methane, and the coal gasification. Other methods of the hydrogen production include the biomass gasification and the electrolysis of the water. The production of hydrogen plays a key role in any industrialized society, since the hydrogen is required for many essential chemical processes. As of 2019, roughly 70 million tons of hydrogen are produced annually worldwide for the various uses such as well refining and in the production of ammonia, methanol, and also as a fuel in transportation. There are four main sources for the commercial production of hydrogen, that is the natural gas, well, coal, and the electrolysis, which account for the 48%, 30%, 18%, and 4% respectively of the world's hydrogen production. Fossil fuels are the dominant source of the industrial hydrogen. Carbon dioxide can be separated from the natural gas with a 70 to 80% efficiency for hydrogen production, and from the other hydrocarbons to varying the degrees of efficiency. Specifically, the bulk hydrogen is usually produced by the steam reforming of methane or the natural hydrogen production methods. The first method is the steam forming. The steam reforming is a hydrogen production process from the natural gas. This method is currently the cheapest source of hydrogen. The process consists of the heating the gas to between the 700 to 1100 degrees centigrade in the presence of steam and the nickel catalyst. The resulting endothermic reaction breaks up the methane molecules and forms the carbon monoxide and the hydrogen. The carbon monoxide gas can then be passed with the steam over the iron oxide or the other oxides and undergo a water gas shift reaction to obtain the further quantities of the hydrogen. The downside to this process is that its major byproducts are the carbon dioxide and carbon monoxide and the other greenhouse gases. Depending on the quality of the feedstock, the natural gas rich gases naphtha, 1 ton of the hydrogen produced will also produce the 9 to 12 tons of carbon dioxide. For this process, the high temperature like 700 to 1100 degrees centigrade, steam reacts with the methane in an endothermic reaction to yield the sun gas that is called the CH4 plus H2O yields the carbon monoxide plus 3H2. In a second stage, the additional hydrogen is generated through the lower temperature exothermic water gas shift reaction performed is at 360 degrees centigrade. The carbon monoxide plus H2O is equal to carbon dioxide plus hydrogen. Essentially, the oxygen atom is stripped from the additional water that is called steam to oxidize the carbon monoxide to the carbon dioxide. This oxidation also provides the energy to maintain the reaction. Additional heat required to drive the process is generally supplied by burning some portion of the methane. Second method is from the water. Methods to produce the hydrogen without the use of fossil fuels involve the process of water splitting or splitting the water molecule into its components oxygen and hydrogen. When the source of energy for the water splitting is renewable or the low carbon, the hydrogen produced is sometimes referred to as the green hydrogen. The conversion can be accomplished in several ways, but all methods are generally more expensive than the fossil fuel based on production methods. The electrolysis is the common method to split the water and yield the hydrogen and oxygen. The electrolysis consists of using electricity to split water into hydrogen and oxygen. Electrolysis of water is 70 to 80% efficient, while the steam reforming of natural gas has a thermal efficiency between 70 to 80%. The efficiency of the electrolysis is expected to reach 82 to 86% before 2030, while also maintaining the durability as progress in this area continues at a pace. Water electrolysis can operate between the 50 to 80 degrees centigrade, while the steam methane reforming requires temperatures between 700 to 1100 degrees centigrade. The difference between the two methods is the primary energy used, either electricity or the natural gas. Due to their use of water, a readily available resource, electrolysis and similar water splitting methods have attracted the interest of the scientific community. With the objective of reducing the cost of hydrogen production, the renewable source of energy have been targeted to allow the electrolysis. There are three main types of cells: solid oxide electrolyzer cells, that is called SOES, ECS, polymer electrolytic membrane cell, that is called PEM, and the alkaline electrolysis cells, that is called X. The SOECs operate at the high temperatures, typically around 800 degrees centigrade. All these high temperatures, a significant amount of energy required can be provided as the thermal energy, and as such is termed as the high temperature electrolysis. The heat energy can be provided from a number of different sources, including the waste industrial heat, nuclear power stations, or the concentrated solar thermal plants. This has the potential to reduce the overall cost of the hydrogen produced by reducing the amount of electrical energy required for electrolysis. PEM electrolysis cell typically operate below the 100 degrees centigrade and are becoming increasingly available commercially. These cells have the advantage of being comparatively simple and can be designed to accept widely varying the voltage inputs, which makes them ideal for use with the renewable sources of energy such as the solar photovoltaic cell. The AECs optimally operate at the high concentrations electrolyte such that the KOH or the potassium carbonate, and at the high temperature open near to 200 degrees centigrade. Now the chemically assisted electrolysis. In addition to reduce the voltage required for electrolysis via the increasing of the temperature of the electrolysis cell, it is also possible to chemically consume the oxygen produced in an electrolyzer by introducing a fuel such as carbon, coal, methanol, ethanol, formic acid, glycol, etc. into the oxygen side of the reactor. This reduces the required electrical energy and has the potential to reduce the cost of the hydrogen to less than 40 to 60% with the remaining energy provided in this manner. In addition, the carbon or hydrocarbon assisted water electrolysis, that is called CAWE, has the potential to offer a less energy intensive, cleaner method of using the chemical energy in various sources of carbon such as low rank and high sulfur coals, biomass alcohols, and the methane, where the pure carbon dioxide produced can be easily sequestered without the need for the separation. Second is the radiolysis. Nuclear radiation can break the water bonds through the radiolysis. In the Mopeng gold mine in South Africa, the researchers found in a naturally high radiation zone a community dominated by a new phylotype of D-sulfatomacalum feeding on primarily radiolytically produced hydrogen. Spent nuclear fuel is also being looked at as a potential source of hydrogen. Thermolysis. The water spontaneously dissociates at around 2500 degrees centigrade, but this thermolysis occurs at temperatures too high for usual process piping and equipment. Catalysts are required to reduce the dissociation temperature. Thermochemical cycle. Thermochemical cycles combine solely heat sources with the chemical reactions to split the water into its hydrogen and oxygen components. The term cycle is used because aside from water, the hydrogen and oxygen, the chemical compounds used in this process are continuously recycled. If electricity is partially used as an input, the resulting thermochemical cycle is defined as a hybrid cycle. The sulfur iodine cycle, SI cycle, is a thermochemical cycle processes which generates the hydrogen from the water with an efficiency of approximately 50%. The sulfur and iodine used in the process are recovered and reused and not consumed by the process. The cycle can be performed with any source of very high temperatures, approximately 950 degrees centigrade, such as by concentrating the solar power systems, and is regarded as being well suited to the production of hydrogen by high temperature nuclear reactors, and as such is being studied in the high temperature engineering test reactor in Japan. There are other hybrid cycles are there that are used both the high temperatures and the some electricity, such as the copper chlorine cycle. It is classified as a hybrid thermochemical cycle because it uses an electrochemical reaction. In one of the reaction steps, it operates at 530 degrees centigrade and has the efficiency of near 43%. Another type of hydrogen production method is the ferrosilicon method. The ferrosilicon is used by the military to quickly produce the hydrogen for balloons. The chemical reaction uses the sodium hydroxide, ferrosilicon and water. The generator is small enough to fit a truck and requires only a small amount of electric power. The materials are stable and not combustible, and they do not generate hydrogen until mixed. The method has been in use since World War I. A heavy steel pressure vessel is filled with the sodium hydroxide and ferrosilicon. Closed, a controlled amount of water is added. The dissolving of the hydroxide heats the mixture to about 93 degrees centigrade and starts the reaction. Sodium silicate, hydrogen and steam are produced. The another process from the water, that is the photobiological water splitting method. Biological hydrogen can be produced in an algae bioreactor. In the late 1990s, it was discovered that if the algae are deprived of sulfur, it will switch from the production of oxygen such that the normal photosynthesis to the production of hydrogen. It seems that the production is now economically feasible by suppressing the 7 to 10% energy efficiency barrier with a hydrogen production rate of 10 to 12 ml per liter culture per hour. The photocatalytic water splitting, the conversion of the solar energy to hydrogen by means of water splitting process, is one of the most interesting ways to achieve the clean and renewable energy systems. However, if this process is assisted by the photocatalyst suspended directly in water instead of using the photovoltaic and an electrolytic system, the reaction is in just one step. It can be made more efficient. Partial oxidation from the fossil fuel. Hydrogen production from the natural gas or other hydrocarbons is achieved by the partial oxidation. A fuel air or the fuel oxygen mixture is partially combusted, resulting in a hydrogen-rich syngas. Hydrogen and carbon monoxide are obtained via the water-gas shift reaction. Carbon dioxide can be co-fed to lower the hydrogen to the carbon monoxide ratio. The partial oxidation reaction occurs when a sub-stoichiometric fuel-air mixture or the fuel oxygen is partially combusted in a reformer or partial oxidation reactor. A distinction is made between the thermal partial oxidation and the catalytic partial oxidation. The chemical reaction takes the general form. The CnHm plus N by 2O2 yields the NCO plus M by 2H2. Idealized example for heating the well and the coal, assuming the compositions of C12H24 and the C24H12 respectively, are as follows. The C12H24 plus 6O2 yields the 12CO plus 12H2, and the C24H12 plus 12O2 yields the 24CO plus 6H2. From the fossil fuel, the another method is the plasma reforming. The Kavner process or the Kavner carbon black and hydrogen process is a plasma reforming method developed in the 1980s by a Norwegian company of the same name for the production of hydrogen and carbon black from the liquid hydrocarbons. Of the availability energy of the feed, approximately 48% is contained in the hydrogen, 40% is contained in activated carbon, and 10% in the superheated steam. Carbon dioxide is not produced in the process. A variation of this process is presented in 2009 using the plasma arc waste disposal technology for the production of hydrogen, heat, and the carbon from the methane and natural gas in a plasma converter. The fossil fuel and another process from the coal. For the production of hydrogen from the coal gasification is used. The process of the coal gasification used the steam and a carefully controlled concentration of gases to break the molecular bonds in the coal and form a gaseous mix of hydrogen and carbon monoxide. This source of hydrogen is advantageous since its main product is coal-derived gas, which can be used for fuel. The gas obtained from the coal gasification can later be used to produce the electricity more efficiently and allow a better capture of greenhouse gases than the traditional burning of the coal. Another method for conversion is low temperature and high temperature coal carbonization. Another process is from the petroleum coke. Similarly to coal, the petroleum coke can also be converted in hydrogen rich syngas via the coal gasification. The syngas in this case consists mainly of hydrogen, carbon monoxide, and the hydrogen sulfide, depending on the sulfur content of the coke feed. Gasification is an attractive option for production of hydrogen from the almost any carbon source while providing the attractive hydrogen utilization alternatives through the process of Another method is the fermentive hydrogen production. The fermentive hydrogen production is the fermentive conversion of organic substrate to biohydrogen manifested by a diverse group of bacteria using multi-enzyme systems involving 3 steps similar to anaerobic conversion. Dark fermentation reactions do not require the light energy, so they are capable of constantly producing hydrogen from organic compounds throughout the day and night. Photofermentation differs from the dark fermentation because it only proceeds in the presence of light. For example, the photofermentation with the Rhodobacter spiraeus SH2C can be employed to convert the small molecular fatty acids into the hydrogen. Fermentative hydrogen production can be done using direct biophotolysis by green algae, indirect biophotolysis by cyanobacteria, photofermentation by anaerobic photosynthetic bacteria, and the dark fermentation by the anaerobic fermentative bacteria. For example, the studies on hydrogen production using H-selenium and the anaerobic photosynthetic bacteria coupled to a hydrogenous donor like E. coli are reported in literature. The Enterobacter aerogenes is an outstanding hydrogen producer. It is an anaerobic facultative and mesophilic bacterium that is able to consume the different sugars, and in contrast to the cultivation of the strict anaerobics, No special operation is required to remove the all oxygen from the fermenter. The E-erogens has a short doubling time and high hydrogen productivity and the evolution rate. Furthermore, the hydrogen production by this bacterium is not inhibited at high hydrogen partial pressures. However, its yield is lower compared to the strict anaerobic like Clostridia. A theoretical maximum of 4 mole hydrogen per mole glucose can be produced by the strict anaerobic bacteria. Facultative anaerobic bacteria such as E-erogens have a theoretical maximum yield of 2 mole hydrogen per mole glucose. Biohydrogen can be produced in the bioreactors that utilize the feedstocks, the most common feedstocks being waste streams. The process involves bacteria feeding on hydrocarbons and exhaling hydrogen and carbon dioxide. The carbon dioxide can be sequestered successfully by several methods having the hydrogen gas. In 2006 to 2007, the Nanologics first demonstrated a prototype hydrogen bioreactor using the waste as a feedstock at the Welch grape juice factory in Pennsylvania. From the other methods, the enzymatic hydrogen generation, the diverse enzymatic pathways have been designed to generate the hydrogen from sugars. The biocatalyzed electrolysis are shown in the figure. Besides the dark fermentation, the electrohydrogenesis is the another possibility. Using the microbial fuel cells, wastewater or the plants can be used to the generate power. The plants is grown and the chopped up plant waste fermentation produces the acetic acid. Then the bacteria consume the acetic acid, releasing the electrons, proton and carbon dioxide. Then the carbon dioxide is produced. Greater than 0.2 volts are added from the outside source. Then the electrons join with the protons and form the hydrogen gas. And lastly, the hydrogen is a clean fuel that vehicles can use. This is the hydrocatalyzed electrolysis process. The biocatalyzed electrolysis should not be confused with the biological hydrogen production, as the latter only uses the algae, and with the latter the algae itself generates the hydrogen instantly. Where with the biocatalyzed electrolysis, this happens after running through the microbial fuel cell, and a variety of aquatic plants can be used. This is the microbial electrolysis cell shown in the figure. This includes the reed sweetgrass, cordgrass, rice, tomatoes, lupins, and lastly the process is the nanogalvanic aluminium alloy powder. An aluminium alloy powder invented by the US Army Research Laboratory in 2017, which was shown to be capable of producing the hydrogen gas upon the contact with the water or any liquid containing water due to its unique nanoscale galvanic microstructure. In the next lecture, I want to discuss the storage of the energy, hydrogen energy, and the transportation of the hydrogen energy, and the advantages and disadvantages of the hydrogen energy. These are the references from where I made the lecture. You should go through these references.